Okay, good morning everyone.
Morning, sir.
Today we will continue the
Morning, sir.
second part of the class on PID control. The learning objective for this session will be explain the difference between proportional, integral and derivative control, which is a continuation of what we did in the last class. And we'll see combinations, that how proportional plus integral and how proportional plus derivative or PID control can be used. And we'll see some applications of this in industry and marine applications. How to tune these controllers, that how to decide on the correct value for all the gain factors which are there. That will be covered. And we'll briefly look at what is called as cascade control and what is called as split range control. To recap on what we did in the last class, first part was that there is a type of control called open loop control, but open loop control has got limitations. Mainly it is because there is no continuous measurement of the control variable. If the load changes, open loop control cannot take care. So if you want continuous control, then it is necessary to have closed loop control. And the first type of closed loop control is called on-off control. But on-off control has got applications like compressor cutting in, cutting out, settling tank filling up. All these are examples of on-off control. But on-off control has got its own limitations. If you want a simple example, if you are told that you can drive only by on-off control, what will be the way to drive? Can anyone answer? If you drive only by on-off control, then how will you drive? Can any of the students answer?
Constant speed.
No, it will not be constant. On-off means
On, off, start, stop.
either you go at maximum speed or you go at zero speed. Either you apply your accelerator full or you press your brake full. Similarly, if you are controlling your direction, it will mean either you go fully to right or you go fully to left. You see an example of open loop like speed pump running or a transfer pump running. Either the transfer pump runs or it doesn't run at all. There is no in-between position. So open loop control has got its own limitation. Closed loop control with on-off has got its own limitations. That is why we have proportional, integral and derivative control. So in the last class we said proportional control is for basic control action, but it has got one limitation called offset. Why is there offset in proportional control? What is the meaning of offset in proportional control?
Because it works only on the present error.
Yes. So in case output is required to be maintained, then a deviation also needs to be maintained. Zero deviation means zero output in the case of proportional control. So in process control, you will end up having a steady state error. Steady state error means if your boiler is running at 20% load, you will have a steady water level. If a boiler goes to 50% load, the steady water level will be lower. It will maintain a steady value, but it will become lower. That is the problem with offset. So if you want to eliminate offset, then integral control is used. So in the last class, we saw how integral control eliminates offset. Moving further, today we will look at derivative control. Now, what is the meaning of derivative control? Here, the controller output is proportional to rate of change in the error, not at the value of the error. Rate of change. Rate of change means if you think of boiler water level, you don't bother about whether the water level is low or is it high, not at the value. You see how fast is the water level changing. Is the water level dropping fast? Is the water level rising fast? That is what matters in the case of derivative control. It is normally considered as a anticipatory control. Anticipatory means it will react faster than proportional and integral. This is the formula. UD means output of the derivative control. KD is derivative gain. And dE by dt. dE by dt is rate of change in error. So it doesn't matter what is the value of the error, and it also doesn't matter what is the duration of the error. Where is duration of error important? Which type of control?
Integral.
Integral control reacts to duration of error. So even a small error can produce large output if the duration is small. That was the principle of integral. Now, if you see on the right hand side, you can see a small sketch. What is on the x-axis is time. Y-axis is called deviation. So, what is the meaning of this line going up like this? The deviation line is going up. What does it mean? It means some error is increasing. It could mean that temperature of jacket water is rising steadily, or it can mean that boiler water level is coming down steadily like this. That is called steady change in deviation. Now, we are saying output of the derivative control depends on rate of change. So, what is dE by dt here? Deviation is E. What is dE by dt? In differential calculus, what is dy by dx?
Slope.
Slope of the tangent. Slope of the tangent is called dy by dt, dy by dx. So here, this itself is a straight line. So what will be its slope? Is it a changing value or is it a fixed value?
Fixed value.
Fixed value. It is a tangent of the angle. Tan of the angle is the slope. So based on the tan of the angle, you will get an output immediately this much. So this much of output comes immediately as soon as the change starts taking place. So the advantage, can you see the advantage? Error is very small here. Error has just started building up at this point. But the output has already become this much. So you are getting a large output. You are getting a large output right at the beginning. This is where the error is beginning to develop and the output is already available. This is the reason this is called as anticipatory control. It is capable of anticipating the problem. So out of the three controls, proportional, integral and derivative reacts the fastest. It will be the first to do. When compared to proportional and derivative, derivative will react faster. This is the meaning. Is this part clear?
But sir, without proportional derivative cannot work, na?
Derivative alone cannot be used. We'll see that. Derivative alone is not used. But when proportional starts building up even a little bit output, the derivative will develop much more than that. So if you can, in this graph, you can see the comparison. You can see the comparison here. Then if you see here again, deviation is rising. How will proportional output relate to this? Error is building up gradually. So how will the proportional output vary?
Gain into error.
No, you multiply by gain, but as the error increases, output will increase. So that is why we say it varies as the height of the deviation curve. Height means this value. That as the value of error increases, this value, this is increasing more and more. This is increasing more and more. This output is also increasing more and more. Suppose the gain is more, what will be the result? Proportional gain is more. How will this graph change? Instead of being like this, it will become more steep. But it will still be a straight line. It will still be a straight line because proportional output depends only on value of deviation. Derivative output is different. You can make out here, derivative output came out immediately. So proportional is slower to respond, derivative is faster in responding because you look at the rate. Here again you see, if the rate of error is more, how does it react? If the rate of error is more, you see this one. Here the error is developing slowly. So what is the output you are getting? This much. What is shown in the black line. Here the error is rising fast. That means the water level is dropping fast, temperature is rising fast. Then the immediate output you get this much. What is the reason for the difference? The reason is it depends on the slope. And which has got a higher slope here out of these two? Black or red line, which has got a higher slope?
Red.
Red line has got a higher slope, so you get a greater output. So this is a major difference between proportional control and derivative control. Derivative control works faster and it works first. Now then why do we have derivative control every time? Is it required in every case? It is not required in every type of case. But wherever the load changes fast, then we need to have derivative control. Main engine is a important example that all the kind of controls relating to the main engine are such that in when the RPM of the main engine increases, the relation is nearly a cubic relation. The relation between RPM and power. What is the meaning of this? And why is it like this? Why do you spend power to propel the ship? When the vessel is traveling at steady speed, what is the reason propeller generates thrust?
Resistance.
It is to overcome resistance. What is the relation between resistance and speed? Is it linearly related or is it more than linear?
Exponential.
It is exponential. And what do you mean by exponential? It is nearly a
V power n plus 1.
It is nearly a square function. If you take frictional alone, we normally write 1.8825 like this. But then when you add the wave making resistance also, you can write for slow ships especially, you can say that the resistance will be proportional to square of the speed. Then to calculate power, you have to multiply by speed on both sides. So what you will get as a relation is RPM to power relation is nearly cubic. The meaning is, whenever RPM doubles, the power will not become 2 times more. Power becomes 8 times more. So so the curve is not going to be a straight line. It is going to, as the RPM increases, the power rises very drastically. So what is going to happen when you increase your RPM? If you go from 0 to 30, it is not an issue. 30 to 40, 50, like that, as we keep increasing, the power increases much more rapidly. So have you noticed this on board your vessels? Many of you might have seen that after pilotage, when you start increasing the speed of your vessel full away, many ships you will find jacket cooling water temperature starts rising rapidly. Have you noticed this in your vessels? Have any of you come across this difficulty? No?
Yes, the bad practice of starting the seawater pump later stage, after half ahead. So we are waiting for that 85, 86, okay. When we started at 85, already it has gone to 90 or something, and so we have to come down, and we are in the Bombay maneuvering from outer anchorage to inner anchorage. So finally they said already the problem was there. So they said 6 knots you have to make, but whereas we are making only 5.5 knots. So they said get out of the tune and don't come for 2 days.
Okay. No, even others would have faced this problem, that as you start increasing the power, there are vessels where even they change the set point of the alarm for jacket cooling water. For maneuvering time alone, they increase because there is a risk of temperature rising too high. So in these kind of examples, you must have derivative control, because if you have derivative control, it anticipates the rise of temperature and it will produce an output earlier. Larger output comes earlier. If you want practical day-to-day example, driving is a very good example, and the way we apply brakes. So when you are driving your vehicle, on what basis do we apply brake? How do you say that I must apply brake now? We normally look at the distance between your vehicle and the vehicle in front of you. As the distance becomes less, you will apply brake more. But you don't go by distance alone. Suppose your vehicle is traveling fast, and in a highway, if you are driving or you're traveling at high speed, you also you should be aware of the rate at which the distance is reducing. If the driver in front of you applies a brake, then you will start approaching the vehicle in front at a very fast rate. So the equation is that not just the distance between the two vehicles, but the rate at which the distance is changing, and you apply a brake much earlier. Otherwise, you'll go and hit. So braking is a very good example of practical day-to-day use of derivative control. And if you go and see how do we adjust this, this is the equation. Once again, there is the derivative gain can be written like this. It is Kp into Td. What is Kp?
Proportional gain.
Proportional gain. Kd is derivative gain. So the relation is this. Td is known as rate time or derivative time. In a later slide, you will see the comparison between the two of them, as graphically you can see. Now, increasing the rate time will increase the derivative gain in all this. Now, what is the advantage of having a large derivative gain? It is like when you have a large derivative gain, large values of error will be prevented. What is the meaning of this? It is that suppose I have a good derivative control. If the water level starts dropping, it will not drop to very low level. Or if the temperature rises, it will not rise to very high values. Will derivative control eliminate offset?
No.
No. because derivative control does not respond to the duration, it will not eliminate offset. So till here, do you have any questions? Have any of the students posted any queries? Or can we move on? If any of you have doubts, you can ask now. Any
Please use the chat mode because there are no queries till now. I think you could use the chat mode, post your queries. Or you can also speak. You can unmute your mic and speak as well.
all right.
नहीं सर, आपने बोला कि ये डेरिवेटिव्स जो है मेन इंजन जैकेट के वहां पे यूज करते हैं, बट सर फिर हम लोग ये यूज क्यों नहीं करते? हम लोग तो फिर मतलब पीआईडी यूज करते हैं ना बेसिकली.
The derivative, the D part is derivative. The reason D is there is because of this problem. Otherwise, you can have only P plus I. Jacket cooling water temperature control is PID control, as you said correctly. Why I is there? What
So
last
that works on the future error.
Not future error.
Reset.
I is meant for eliminating offset. It means whether I run my engine at 70 RPM, 80 RPM, 90 RPM, 100 RPM, any speed I make my voyage, if I ask for 85 degrees centigrade in jacket water, I will get 85 degrees. There will be no persisting error. That comes only because of the integral part. So if suppose I don't put integral and I have only P plus D, then what will happen is you will get quick response. But as the speed of your engine increases more and more, increases means suppose you are making a voyage at 60 RPM, then you will get a different jacket cooling temperature. Like suppose I set always, I set my desired value of 85. Then I'm making a voyage at 70 RPM. Then I will not get 85, I will get 88. With the same set point, if I make a voyage at 90 RPM, temperature will increase to 90. That is called offset. And to eliminate offset, you can put I. So it becomes P plus I. But if you don't put D, you will face a problem like what happens during maneuvering. That is the difference. Is it clear?
Yes sir.
So it is PID. See, PID is used for, that is the reason I said main engine control mostly as PID control. Okay, can we move on to the next one? All right.
Yes sir.
So derivative control cannot be used alone. What is the reason? It is because suppose the error is constant. What happens then? There is a persisting error. Then what is the rate of change?
Rate of change will be nil.
If the error is constant, then the rate of change is 0. So derivative output becomes 0. Or in case, imagine water level in the boiler is going down very, very gradually. Then the output will be very, very small if you use derivative control alone. That output will not be enough to overcome, for example, friction in your actuator. So what will happen is the entire boiler water level can go down and still you will get no correction at all. So out of the three, proportional can be used alone. Common, it is used alone regularly. Integral can be used, but usually not done because its initial output is poor. Derivative can never be used alone. So you will see either as P plus D or PID. Okay, so where will you use proportional plus derivative? It is where quick correction is required. Driving in a city is an example. Now, if you drive in a city, do you require integral control? What do you think? Will integral control be required if you are driving a vehicle inside city?
Not required.
Because integral control is for steady state. When you are driving around inside a city, there is hardly any time you will maintain a steady speed. Most of the time, speed will be increasing or decreasing. So what you need is quick response. So our brain is already wired into all this. What I mean to say is that you don't have to learn PID control before you start driving a vehicle. Nobody has learned PID control before driving a vehicle. Then how is the brain capable of learning all this? Because that is what learning teaches. But what principle brain applies is the same thing. It is based on the derivative principle. Can you have rudder angle control? When you are controlling the position of a rudder, do you require integral control?
Yes.
Yes, sir. Because we have to reduce the offset.
No. See, in integral control, if an output has to be maintained even in zero error, only then you require integral control. Error becomes zero, I still need an output. That is when you require integral. So you take an example, jacket cooling water temperature. What is the temperature you want to maintain? On board a vessel, you want to maintain 85 degrees.
80
I'm
degrees.
maintaining 85 degrees. But the three-way valve has to have a output, right? It has to be in a particular position. Do you agree?
Yes, sir.
Yes. So in jacket cooling water control system, error becomes zero. I still need an output to keep the three-way valve in a particular position. But in steering gear, you think that rudder has reached the required angle. I want 20 degrees in rudder position. Rudder reaches 20 degrees. Do I still need an output?
No, sir.
I don't need. The pump can go to zero stroke.
Yes, sir.
When the required rudder angle is reached, pump can go to zero stroke.
Yes, sir.
An output to be generated in zero error condition for rudder control. So if we can work with only proportional, rudder angle control still works. But to make the response quicker, we can put
Derivative as well.
P plus D. So most common combination of steering gear control will be
இது போட்டுக்கிட்டா டே காதுல போட்டுக்கிட்டா
the rudder angle control is P plus D. But your autopilot control, where you are maintaining the course of your vessel.
PowerPoint presentation தெரியுதா?
தெரியுது.
Mute please, except when you are asking questions. So this for the autopilot control, where you are maintaining the course of the vessel, PID. Okay. So this part we already discussed. If I use PD, will offset be eliminated? Offset cannot be eliminated. Integral is required.
இங்க இருக்குமா இங்க இருக்கு.
Students, please mute your mics, except when you are asking. Thank you. So this graph shows proportional plus derivative. So what do you see here is a sudden increase in load. So imagine this is some value which is changing. So you see temperature, this is what you need to maintain. So temperature is dropping like this. As the temperature is dropping, proportional control will generate an output like this. So the output of the proportional control increases steadily. But what happened with the derivative control? You get the output immediately. So proportion alone gives this much, derivative gives this much. So together you get like this. But you can see offset is still there because integral is missing. So quick response is possible, but you'll still get steady state error, P plus D. Now, there are these gain values called Kp, Kd and Td. All these are the values which you have to understand a little bit if you want to understand how tuning is done. What is Kd?
Derivative gain.
It is derivative gain. It is written as Kd is Kp into Td. Td is known as rate time or derivative time. And you can make out from this graph on the side that again you are seeing deviation is rising gradually. This is called as a ramp change. What is the meaning of a ramp? It is not a sudden change, it is a gradual change. So when a ramp change takes place in error, proportional output also will increase gradually like this. So proportional depends on the error. But what will you get with derivative? You will get the derivative output immediately. This much you will get immediately. So if you take an example like valve opening, if this derivative control opened the valve by 2 millimeter immediately, then proportional control will take this much of time. It cannot do immediately, it will take this much time. So the time taken by proportional control to match whatever derivative is doing, that is called as rate time, also known as derivative time. So once again the issue is derivative works first, proportional will follow, it will take time. So the time taken by proportional control to produce whatever the derivative control has done is called as rate time. And in the controllers, this is what is adjusted. Many of you would have seen there are controllers where derivative control is also there. This is a picture of a P plus I control. Why do we use P plus I? It's because offset should not be there. Have you all seen this type of controller on board a vessel? Many of you would have seen. So here is the reset time. In this part it is showing reset time. Here it is showing the proportional band which you can adjust. So this part is for controlling proportional gain. This part is for controlling integral gain. Here you can see this is a proportional band. This is the integral time, or also known as reset time. Have you seen this part in your vessels? This is a relay. This is a pneumatic relay for increasing the output to the actuator. So these are the dials which need to be adjusted when you are tuning your controller. We'll come to that tuning part. So if you want to compare integral time, this is the meaning. with when deviation takes place, suddenly, this is called as a step change, then proportional will immediately react and you will get this much of output. But what will happen to integral control? Integral control will take time because integral gain is like this. It is proportional gain divided by integral time. So here, between proportional and integral, proportional is first. Integral takes time. So the time taken by integral control to produce the same output as a proportional control, that is called as integral time or reset time. So these are the values which need to be adjusted. Practically what it means is that if I increase the integral time, then this graph will be more gradual. So it will take more time to make corrections. You take simple examples. Many of you would have sailed on tankers. So if you have a tanker which is a boiler which is supplying steam to cargo turbines, if the cargo turbine speed is increasing or more turbines are brought into use, the water level will come down. You agree?
Yes.
Water level will come down, then it will again come back to the normal level. Have you noticed it? If your controller is working correctly, it will drop, then it will come back to the original level. Similarly, steam pressure will drop and then it will come back to the original. But if it is taking too much time to come back, it means this reset time is too high. Then by reducing the reset time, you can recover the original water level faster. Is this part clear? Because these are all practical steps which you can use on board a vessel to solve problems. So very often on board a vessel, control problems come under two main categories. Either the controller is too slow in response, there's a lot of hunting. Have you seen this?
Sir, you're speaking about this swelling and shrinking in the boiler.
No. That we're not touching that at all. That will be in the later class. Swelling and shrinking comes because of changes in water temperature. That is dealt with a different class where we'll be talking about function-based control. Now what I'm saying is, whenever you have P plus I control or PID control, your desired value will be reached. Correct? If you are asking maintain half drum in my boiler, the controller will maintain that half drum. But initially the level will definitely go down. As you start more load, definitely it will go down. But eventually it will come back. Maybe after 4 minutes or 10 minutes or 6 minutes, it will come back to original. So if you feel it is taking too much time, then in your controller, you should reduce this value, which is called as a derivative time. Integral time. This value. If you reduce reset time, you will recover zero error condition faster. That is the purpose of this. Okay, shrinking and swelling will cover in a different class. That comes later. So this is P plus I. Once again, same way, load is increasing, level is dropping. Proportional control gives this much output. Integral control gives this much output. And resultant is here. Now you can see, this is one more useful graph you can see. Load is increased. What is the offset here? Here the level dropped or temperature dropped. Is there any offset now here?
No.
No, zero offset. It is again reached. So your controller should have more output. The valve should have opened more. And you can see that extra output is coming from the reset or integral control. If error is zero, what will be the proportional output?
Zero.
It will be zero. So who's opening the valve more, or who's controlling the actuator more?
Integral control.
Entirely from the integral control. So in any steady state condition, if you have integral control, output comes entirely from the integral part. Proportional error will be output will be 0. Now this is where you have a combination of all of them. PID control, that proportional, integral, and derivative. So all the gains are shown. So it is what is important in this point is that this is a they are all added up. Proportional, integral, derivative, all the outputs are added up. So suppose the derivative part alone fails, then what will happen to the controller? Will it fail to work, or it will still?
It works.
It will still work.
It will still function like a
PI controller.
PI controller. That is the difference. So it is still capable of working. Now, if your integral parts fails to work, you will start seeing offset. Before you would have maintained the same value, now you will start seeing offset. So this graph shows all three put together. It is the same as the other one. So advantage is you will have no offset under steady state condition, main engine governor, jacket cooling water temperature control, viscosity control, purifier temperature control. All these are examples of PID. And this, as we said before, under steady state control, only the integral output will remain. Others you can see. Derivative 0. Why it is 0 now?
Steady state.
Because the error is not changing. Why is proportional output 0?
Error is 0.
Error itself is 0. Only integral is producing the output. So both these have got 0 output, and only integral produces the output here. That is the principle of this. So you can understand that all these three are parallel control, and if one fails, other will continue to function, but it will work differently. This is the final actuator. All of you would have seen this. This part, what is this part called?
IP converter.
No, this part is the positioner. This is called a valve positioner.
Valve positioner, sir.
To keep the valve in the required position. Okay, so you can see this part. Now, how to tune the controller? Tuning the controller means setting correct values for the gain. What are the different gain values you need to adjust? What is the gain? What is the adjustment for proportional?
KP.
And adjust.
KP.
Either KP or it will be PB. What is PB?
Band. Proportional band.
Proportional band. So, depending on the type of controller, your controller will say either KP, like electronic controllers often have option for both, but pneumatic controller will have only one. And most pneumatic controllers you would have seen has proportional band. And the relation between band and gain is, it is the inverse. If proportional gain is more, it is the same as band is less. So there are two ways means same thing, but two different ways of adjusting proportional. That is KP and PB. How do you adjust integral gain?
Reset time.
It will be either, it will be written KI. KI means integral gain, or it will only say TI. TI means reset time. Similarly, how do you adjust derivative gain?
KD.
It will say KD or
TD.
TD, like this. But you would have noticed TD comes in the numerator, and where does TI come?
Denominator.
It is coming in the denominator. So the principles are different. So if you have a PID controller, there is a way of tuning it. And one of the most widely used tuning methods is called Ziegler-Nichols method. It is a very practical method. There is no mathematics involved. You can do it directly in the plant. And onboard your vessels, this is also something you should do. In case, suppose for example, your controller is completely defective and you order a new controller and a complete controller comes, that controller will have to be adjusted for your vessel. So at that time you need to adjust this. Or you may also come across situations where to overcome defects which are elsewhere, all the dials in your controllers have been turned. So just think of a simple example. In a pneumatic controller, if the output line, the line going from your controller to the actuator has got a leak, what will be the result of this?
Sluggish output.
Sluggish output will be there. So I don't have time or I am not aware that there is a leak. So how do I compensate for this? If the output is sluggish, what should I do?
Increase the integral gain.
I should increase gain. If I increase gain, then the output will be increased. But later on, somebody else comes and he solves this problem, that the leakage is solved. Then what happens is the gain will be excessive. So what happens is that in lot of vessels, the adjustment itself can be wrong. Because the adjustment is wrong, again tuning may be required. So the understanding tuning is important. It is not a difficult principle. If you can see it, it will be like this. So first part is remove integral and derivative action. What is the meaning of that? Increase TI to maximum. Why should you increase it to maximum? Because it comes in the denominator. And reduce TD to minimum because it comes in the numerator. Then if you do both of them, what happens to the controller is it behaves like a proportional controller. Yeah, integral and derivative action is removed. Behave just like a proportional controller. What should you do then is you start increasing KP. If you increase KP, what will be the result? Gain is increased more and more. After some time, it will start hunting. Cycling means it will start hunting. Excess gain causes hunting. We discussed in the first class. Or if you have a proportional band, then your band should be reduced. Either way, it can start hunting. So what you should do is, you should note down the gain value where the hunting is taking place. So for example, in the dial, it might show 2.3. That is the gain value at which the cycling is taking place. Similarly, if proportional band is adjusted, then you have to note down the band value. So it could say, for example, 60%. At 60% or 50%, the cycling is taking place. So you have to write down that value. Then you have to write down what is the time period. Cycling time means your actuator valve is going to full open and then to full shut. Complete full open to full shut position and then back to full open. That full up and down movement. That is called as cycling movement. Full open, full shut, back to full open. This period has to be noted down. This is the only two readings you have to take. One reading is the gain value, other reading is the period. So once you take out, note down these two values, then what is required is, this is the way you set. If your controller is only proportional, then set KP as 0.5 or half of KP cycling. So in simple English, it will mean I will turn the dial till the hunting is taking place, then I will turn it back by half. Are you able to understand this part?
Yes, sir.
Increase the gain, and then finally what you should leave is half of that value. So if 2.5 is causing hunting, then I will set it as 1.25. If the controller is only a proportional controller. But if your controller is a P plus I controller, then you have to set like this. The proportional part will be almost same. Integral part you have to set like this. What is TC? That is the cycle time. Cycle time should be divided by 1.2. So, for example, if the valve took from full open to full shut and back to full open, if the valve took, let us say, 12 seconds, then you have to set this at 10 seconds. 12 divided by 1.2. Like that you have to set. And if your controller is a PID controller, then this is the way the values are set. So this is a very standard method. You can see it everywhere. Very often the controller itself comes with this, these details, how to set. It is not a difficult principle. Only thing is, if you are doing it with your plant running, you should be cautious that the values don't reach dangerous levels. The temperature should not go too high or the level should not go too less. So for PID, these are the setting values. Okay, you can make out here also, derivative time will be much less compared to the integral time. Any questions about this tuning part?
Sir, can you show it from the picture of the controller?
If you see in the controller, it only means you are turning these dials, that's all. This dial is for proportional band. So if I keep reducing the band, then the hunting will start. And I should note down at what value the hunting is starting. And finally, I should set it 2 times that, if it was only proportional. I should cause it to hunt, then I should change it. Similarly, derivative time I should set by this, not derivative, sorry, reset time.
Reset time.
This you don't adjust before. Because remember, this you have to adjust for making it to proportional control. So where should I keep this value in the beginning?
Maximum.
I should keep this to maximum. When I keep this to maximum, it behaves like a proportional controller. So I've turned this to maximum. After that, I start reducing this one. This is the proportional band. I start reducing it till it starts hunting. And then I have to turn it back and keep it the way like this. So if you think of PID control, I should keep it at 0.6 of the gain value. If it was gain and band are just inverse. So if you see, if it is 0.6 here, it will become 1 by 0.6 for the band. That is all the differences. But either way, you have to set for gain here, and TI is what you should set. Whatever the cycling time, we keep half of that here. And derivative time, we keep 1/8 of that. So if it took 40 seconds, then 40 divided by 8. That is the time you should keep for derivative time. Is it clear? Okay, move to the next one. Then what is cascade control?
VRV sir, Jagdish wants to speak, sir.
Yeah, go ahead. Tell me, Jagdish.
I think he wanted to inform me about 5 to 10 minutes to go.
Fine.
Only for information.
I'm watching.
Okay. Thanks.
So cascade control is where there is a master controller which controls the variable, and this is where you will set the desired value, and then it will go as a set point to another controller, which is called a slave controller. So the slave controller will be controlling another variable, and it is a slave controller which moves the actuators or correcting unit. So instead of the master controller doing the job directly, it will be done by master and slave. And boiler combustion control is a very good example of it. In boiler combustion control, what are you supposed to maintain? What is the process variable you have to maintain?
Fuel oil pressure and airflow.
No. That is not. No. What is a controlled variable? What are you supposed to control in boiler combustion? See, what is corrected is different. What is controlled is different. We explained it in the first class. I got a boiler combustion control. What is its job? What is it supposed to maintain?
Air fuel ratio.
No. Its job is to maintain
water level.
No, combustion water level is different. Combustion control is for maintaining steam pressure.
Steam pressure.
Steam pressure.
Pressure. So I may be running one turbine, I may be running 3 turbines, but the boiler pressure has to be maintained at 16 bar. That is the meaning. So to maintain boiler pressure at 16 bar, what is the corrected value? What should you increase? What should you? There are two different variables to increase. One is the fuel oil flow.
Airflow.
Right? One is fuel oil, and what is the other one? Other one is airflow. So I need to control fuel and also need to control airflow. So the idea of master-slave control or cascade control will be the steam pressure controller will give its requirement to 2 other controllers. What are the 2 other controllers? One is for airflow, other is for fuel flow. And each of this controller, which is fuel flow controller and airflow controller, will maintain these 2 values. The fuel flow controller job is to maintain the fuel. Airflow controller job is to maintain the airflow. And both these slaves will get their input from this, from the master controller. So you will have, instead of having a single controller, you will end up having 3. So why should you invest in 3 controllers like this? The advantage is that the slave controller will take care of its own responsibility. That one slave controller job is to maintain the airflow, other job is to maintain the fuel flow, and it will be taken care of by each of them. Any disturbance in that loop, it will take care by itself. That is the idea of master-slave control. You also have, these are the issues which you should keep in mind whenever you are discussing any issues with the controllers. Number 1 is this. Whenever you have problems, suppose jacket water is going up or water level is coming down, you are noticing an issue, go to the actuator first. See whether the correcting unit has reached its correct value. If it is not reached if it's already in its correct position, the controller has done its job. Like simple example is jacket water is rising. Then instead of fiddling with the controller, you should go straight to the 3-way valve. What should you note now? Jacket water temperature is going on rising. So what should you see in the 3-way valve? Anyone answer? With the rising water temperature, where should the 3-way valve be?
Towards cooler.
Yeah, bypass should be closed and cooler side should be fully open. If it is already there, then the controller has done its job. There's nothing more the controller can do. But if it has not reached that value, then you see there is an issue there. Yeah, so you have to always work backwards from the actuator or the correcting unit onwards. You have to work backwards. What is the meaning of failing mode of an actuator? Is that will it close in a failed condition or will it open in a failed condition? Which way will it send? This has to be understood. Control valves are open. They can close while going up also. They are not like ordinary valves you see in pipelines. This you should not forget. All engineers should be aware of changeover procedures. That when you are changing, if automation is not working, if you want to go to manual mode, engineers should know how to do this changeover procedure. Whenever there is an emergency, reduce the load first. It will always give you time, rather than trying to fiddle with adjust the controller. Then if you are going to touch the controller, you must ensure instruments are calibrated correctly first. Instrument calibration is a very important principle. Everyone should understand this. Maybe in later classes we'll take this up, that how to calibrate your instruments correctly. Whenever you make any adjustment, do it in small increments, not suddenly, large values. Give time for the system to stabilize. Actuator movement also has to be checked and calibrated. That is actuator moving from fully shut to fully closed condition. That has to be checked, calibrated. And most important is that when the controller is working, don't ignore it. This is a mistake made in lot of applications, lot of vessels, that when the automation is working, the engineers are not giving enough attention to this. So when they start giving trouble, you will not know how to correct. So please observe your controllers when it is working well. Any question?
Sir, that Ziegler-Nichols method.
Yeah.
What you told about the tuning.
Yeah.
How did they finalize this value, that KPT?
That is what I was telling. No, you finalize based on the way the system is behaving. So you when the controller comes to you, the dial different positions. Correct? Dial will be in different positions. What you should do is you should do like.
No, sir. I'm just asking about that reset time. You had given that TC by 2, and is that a standard value or what?
Yes. These are all. See, this one is a Ziegler-Nichols method is an empirical method. Empirical means not based on mathematical derivation. This is based on how these PID controllers work in general. So this is the standard values for any type of PID controller. It will work. So whatever setting, it will come from the factory with some values. Or in your own vessel, you might discover that the dial has been turned to one extreme end or the other extreme end. It will be in some other position. So you have to just go through these same steps, and then you can set according to this value. So if the cycling time, here it is telling, no, cycling time, here it is telling cycling time is for integral control, you must set TI is TC divided by 1.2. The meaning is that if the valve is taking 12 seconds, just for understanding, I'm saying the valve took 12 seconds to go from fully shut back to fully open. Then I must turn that integral time dial to 12 divided by 1.2, which will be 10 seconds. That is the meaning. This is in case of the controller is only P plus I. But if it is a PID controller, then you will set it as 12 divided by 2. So you will set it as 6 seconds, like this. That is the difference. So this particular technique doesn't depend on the brand of the controller. This is the same for all type of controllers. All PID controllers, whether it is electronic or pneumatic, you can use the same method. Is it clear?
Yes, sir. Thank you.
Any other questions? Okay. Any questions, Subra? Any questions are there?
Hello.
No, sir. Nothing on the chat. But I think we got one participant asking question.
Yeah, please go ahead.
Hello.
Yeah, go ahead.
Sir, Jay here.
Go ahead.
Sir,
as we know, we can use PI controller separately, we can use PD controller separately. So can we use ID controller also?
No. Because it will create a lot of instability. So proportional will always be there. There is no controller without proportional. Proportional is a basic. It is like having rice or chapati. Others are like side dish.
Okay, sir. But when you were explaining, at that time you said derivative can also be zero, and the proportional will also be zero, and only integral is giving out the output.
Correct.
So we can also use ID also, because if derivative is getting means the value of derivative is zero, so I will give its output.
No. Your initial response issues will be because see the derivative control is a very, very fine adjustment. If you see the values that are given there, derivative is a very fine adjustment. So it is never used alone, and it is not used along with I alone. You will always have proportional first. In addition to proportion, you can do the other things. That's the reason. If you try to say I will not use proportion alone, then your system will be very unstable. So you need to have proportional first. Then on top of it, you can have integral or derivative as required.
Okay, sir. Okay.
Because what you saw, that integral alone is giving the output at the end. Steady state condition. But, you start your main engine, then only you reach your full speed. No.
Yes, sir.
So in between, there will be a lot of unstable conditions. So during these unstable conditions, if you don't have proportional, you will get a lot of instability in your system. So if you don't have anything called I plus D, you have P alone, you have P plus D alone, or P plus I, or PID.
Okay, sir. Okay.
Any other questions?
So there was one question, possible to relate PLC with PID controllers?
PLC is a logic controller, programmable logic controller, but any PLC controller can also be PID controller. PLC also executes programs. It just executes mathematical equations. So you have PLC controllers which are also PID controllers. Definitely you can use. PLC is only the hardware part. So in the PLC controller, if you can write the PID program, you can definitely use. There is
okay, sir.
If you go in the equations, there is a difference between the derivative equation that you write. That is all there is. The input of PLC controllers, or the way PLC works, is it is a digital machine. So it works by step changes internally. So there is a small difference mathematically. Otherwise, you can definitely use it.